sky from here in North Georgia, a day sky. This is the morning of March 5th around 8 a.m., just a bit after sunrise. We're facing south, so that curving line on the bottom is your southern horizon, and towards the top middle of our screen is looking straight overhead. Now, we can actually see the moon out during the day. We see the moon out during the day just as much as we do at night. It's between south and west there. That is a waning moon. You see the moon out more during the day when it's waning. That means it's going from a full moon to a new moon. We're going to zoom in on the moon so we can take a better look at it. This will be kind of like we're looking at it through a telescope. We do have telescopes here at the University of North Georgia at our observatory. It's about 4 miles off campus. Right now we have a brand new building and telescopes that just finished construction, but they haven't been open to the public yet. There are going to be live streaming telescope operations looking at the night sky on the night of March 5th and 6th during the Dahlonega Science Festival. That's if the skies stay clear. You can check out the page for the Dahlonega Science Festival, dahlonegascience.org/festival, to get more information on that. But for now, we'll zoom in on the moon. So here we are at the moon. The Apollo 11 mission to the moon in 1969 was the first time that humans stepped on another world. The moon is the only place we've walked besides the Earth. Neil Armstrong and Buzz Aldrin took the lunar module down to the lunar surface. They had to break away from the command module that was orbiting around the moon. And then to return, they took part of the lunar module back, redocked with the command module. Going to and from the lunar surface, it requires complex orbital maneuvers, mechanics that are calculated by hand as much as by machine. And the hand calculations were done primarily by women, including Katherine Johnson. Katherine Johnson was one of several women highlighted in the book and movie Hidden Figures, a so-called computer making computations for NASA. Katherine Johnson was a mathematician, an expert in geometry. She graduated high school at 14, college at 18. She was particularly crucial to the early spaceflight programs. She worked on the Apollo missions and she did trajectory analysis, both for the first American to go into space, Alan Shepard, and the first American to orbit Earth, John Glenn. She also happened to be a black woman, working in traditionally segregated workplaces, both by race and gender. But Johnson was a leader as well as a mathematician. She started showing up to meetings that she was told women did not attend. She told her male colleagues that she did the work, so she belonged there. She was the first woman to put her name on a report in her division. Her work often included making backup charts and procedures for navigating when electronics fail in space. Her work was needed during Apollo 13 in order to bring astronauts home safely. She worked at NASA for 33 years, pioneering how we travel through space, how we got to the moon. Katherine Johnson passed away at the age of 101, but she was not the last woman to do pioneering work in science. She left a legacy many young scientists follow. She was also not the first woman to wonder about the skies. We'll turn our attention to another object that dominates our days, the sun. First, we'll zoom out from the moon. The sun is the source of the light and energy we need on Earth to live. Let's fly out to see the sun up close, our closest star. It'll get dark for a moment. We'll bring up the sky on Earth, this time facing east, facing the sun. We'll lift off. Traveling roughly 93 million miles through space. Here we see our sun close up. 109 Earths would fit across its width, and it would take over 1,000,000 Earths to fill up its volume. It's active with material streaming off of it all the time. Today we study the sun from far and near with spacecraft that monitor its activity around the clock. Let's take a look at a video. It's made by many pictures that were compiled from the Solar Dynamics Observatory. We'll bring up 3 ranges of high-energy ultraviolet light. The first range is showing us spicules, small grass-like features in the plasma, little jets that last 5 to 10 minutes. Now we're transitioning to a different range of light. This is showing coronal holes, areas where it's a bit cooler on the sun. And finally, we'll look at the longer strands of plasma arcing above the surface. Understanding the sun and its potentially hazardous changes in activity, it requires looking at different types of light that are given off by the sun, learning everything we can from that light. When we spread out the light, what we get is a rainbow. And that's what we see here in this picture. This is a detailed photograph of the rainbow of the sun across visible light, like what we see with our eyes. But what you'll notice here is there are dark lines throughout it. Those are caused by elements that are in the sun's outer layers. And this rainbow here, we call it a spectrum. It acts like a fingerprint that can tell us what elements are present in the sun. It's not quite as simple as just looking for the fingerprint of an element, though. We also want to know how much of different elements are in the sun. What is the sun made of? And the sun is a star. What are all stars made of? That was a question that was answered by another computer. That is a woman, this time not working for NASA, but working at Harvard Observatory in 1925. Her name was Cecilia Payne Gaposhkin. She was one of many women who worked at Harvard Observatory. Some started in the late 1800s, some worked in the early 1900s. They were a group that were computers, this time at Harvard Observatory, and started by Edward Pickering. Let's take a look at a picture of some of the women in this group. Edward Pickering was an astronomer at Harvard Observatory who needed as many people as he could to process the photographic plates that were being produced by the observatory. They were containing hundreds of thousands of stars that they wanted to compile data on. He hired women because he could pay them a lot less and get more staff. He did also feel that his first male assistant was incompetent. He thought his maid could do a better job. So he hired her. Wilhelmina Fleming was his former maid and the first Harvard computer. Now, Cecilia Payne here, she wrote her thesis to get her PhD, finished in 1925. It was not a simple cataloging of data like a lot of the computers were expected to perform. She did an analysis, calculating from the spectra of stars she examined the amount of different elements that were present in the stars. The popular science of the day had concluded that stars, at least our sun, were just similar to Earth's crust. They seemed to have oxygen, silicon, and aluminum. Why not in the same amounts as we saw on Earth? Almost like the sun was still just made of rock. But Payne found something very different. She found that the simplest elements, hydrogen and helium, were far more abundant in stars. Payne's work would eventually be confirmed, and the masses of the different atomic elements in stars throughout our universe seem to mostly be hydrogen and helium. Only 2% of that mass is all other elements combined. The composition of stars, Payne's method of deriving it from the rainbows of light, it forms a fundamental pillar on which all of our astronomy knowledge stands. It took until 1956, 31 years after completing her thesis, for Harvard to finally make Payne Gaposhkin a professor. She was the first female professor at Harvard. Let's return to our sky from Georgia, this time going to a dark night sky. We're looking at the sky from North Georgia on March 5th. This time it's 8:30 p.m. We're looking at a night sky, a bit after sunset. We're still facing our southern horizon, and we're going to look for a constellation. Constellations are areas of the sky. We look for bright patterns within them to identify constellations. And we're going to start with a constellation made of mostly bright stars. Easy to find, pretty famous. Orion the Hunter. We look for Orion by looking for 3 stars of his belt. Above it are 2 stars that are his shoulders, and beneath it are 2 stars that are his feet. There's an outline so you can see the shape of Orion the Hunter. I'll put up some artwork as well. Orion here is coming to us from Greek and Roman mythology, and he's a super strong giant. When you see him in the real sky, he will look very large. Hanging off of Orion's belt is his sword. I'll put up a marker for it. It is a nebula. Nebula is a word that means cloud. So it's actually a star-forming region. It looks hazy or cloudy because it's filled with actual gas. It is like a cloud of gas in space where stars are being born. Now, spectra, those rainbows of light, they give us insight into clouds of gas as well as stars. So we're going to fly out to the Orion Nebula and see it closer up and find out a little more about it. It will get dark for a moment. We'll bring back up our sky. And lift off out to Orion. The Orion Nebula is 1,300 light years away. That means it takes light 1,300 years to make the same trip. We'll be leaving our solar system entirely. And here we are, as we start to pan around the nebula, you can see its 3-dimensional shape. It has this carved out cavity, almost like a bubble there. And that shape is caused by the massive stars that are down in the center, where you see that yellow color. The massive stars have strong winds of material that are blowing off of them. How do we know when stars are more massive or less massive, essentially more heavy or less heavy? We can compare their properties, brightness, color, the dark lines from the spectras of stars. It lets us figure out the temperatures and the masses of the stars. The spectra are important to study in detail. Classifying them can tell us what type of star we're looking at. Classifying stars by their rainbows, their spectra, was the life's work of several of the Harvard computers. But Annie Jump Cannon developed a system that astronomers still use today. Here we see Annie Jump Cannon. She started working as a Harvard computer in 1896, before Cecilia Payne. She classified almost 400,000 stars just by looking at their spectra. The most massive types of stars are the ones shaping the center of the Orion Nebula here, and they're called O-type stars in Annie Jump Cannon's classification system. What this means is that they're over 15 times as massive as our sun, and at least 40,000 times as bright. They burn hotter than the sun. They burn through their nuclear fuel at their cores, fusing it together, much faster than our sun does, living only a few million years compared to our sun's 10 billion year lifetime. There's a lot we can learn when we organize stars by their properties. Jump Cannon also discovered 300 variable stars. These are stars that change their brightness regularly. Let's go back to our night sky and look for one of the most famous stars in the sky. It also happens to be a variable. We're bringing up our sky from North Georgia on March 5th, just after sunset, 8:30 p.m. This time, however, we're facing north. So the northern horizon is along the bottom of the screen. Our top of the sky is still sort of the top middle of our video here. Now, there is a very famous constellation between north and east low in the sky. You may know it as the Big Dipper. We look for the Big Dipper by looking for 3 stars of the handle and 4 stars of its cup. I'll put up an outline here. It's actually in a constellation called Ursa Major. Ursa means bear, so it's the Big Bear constellation. And the Big Dipper is easy to spot in the sky. We often use it to find the Little Dipper. If you're looking at the cup there, the 4 stars of the cup of the Big Dipper, the end 2 stars of the cup, they're higher up in the sky here. If we imagine a line through them, they will point us to a star that stays north, Polaris, the North Star. So Polaris here is also the end of the handle of the Little Dipper. So the Little Dipper has a very faint handle of 3 stars that ends in Polaris, and then there's a faint smaller cup. I'll put up the outline there so you can see it. It's a lot harder to spot the Little Dipper. It is in Ursa Minor, the Little Bear, but it's a lot harder to find the stars in it. So we usually look for the Big Dipper first, and it can point us to the Little Dipper and Polaris. So Polaris there is the famous star I wanted to talk about that's also a variable. It's actually not the brightest star in the sky. In fact, you'll remember most of the stars in the Little Dipper are somewhat faint, a little harder to spot. Polaris is special instead because of its location. It's almost directly above the North Pole of the Earth. And so that means as the Earth turns, everything in the sky appears to rise and set. All the stars rise towards the east, in the eastern half of the sky, and they set towards the west. Polaris is the only star that doesn't move around much, so it can lead us north. Polaris is a variable star. And we're going to take a look at an animation that shows us variable stars, what they would look like close up. What we'll see here is the star, and it'll change in its color and size along with brightness, but exaggerated here. But what happens is the star periodically puffs up, getting cooler and redder, and then it will contract back down, getting hotter and bluer in color. This happens inside of variable stars because of the fusion happening inside of them. Elements fuse together, making energy and light. But normally in stars, this happens in the core. But in a variable star, the core is likely now dead, and it'll happen instead in thinner shells around the core. And this is just less stable. Polaris is what we call a Cepheid variable star. And that means that the amount of time it takes for it to pulse, for it to change its size, it will be over the course of days to weeks. One of the Harvard computers we'll see here is Henrietta Swann Levitt, and she worked very famously on Cepheid variable stars, kind of like Polaris. She worked alongside Annie Jump Cannon. She discovered about 2,400 variable stars. She wasn't content with just cataloging them. She noticed that the pulses of the variable stars were not arbitrary, they weren't random, they corresponded to the luminosity of the star. That is, the brightness of the star if you were close up to it. We can only know that luminosity of a star if we also know how far away it is, the distance. We can get that by triangulating stars using geometry, but only for a small number of stars, especially at the time that Henrietta Swann Levitt was working. Getting the luminosity another way, through easily measuring just the timing of the pulses of stars changing their brightness, this meant a whole new way to find the distance to those variable stars. The pulses could be measured for variable stars that are in other galaxies too. Finding the distances to other galaxies had never been done before Swann Levitt. She gave us a measuring stick for the universe. Other astronomers like Harlow Shapley and Edwin Hubble, they used Swann Levitt's work in order to show for the first time that other galaxies exist at far distances outside our own Milky Way. Some of them are billions of light years away. We now know through the work of many women that the universe is impossibly large and that galaxies their light takes billions of years to reach us. We know how to classify stars. We figured out what they're made out of, how to study primordial clouds and stars from their rainbows of light. We even set foot on another world, our moon, thanks to the work and brilliance of many women working in astronomy, wondering about the sky.